Hello everyone, my name is Matthew McLennan and I'm from Pacific Rim Laboratories in Surrey, British Columbia, Canada. And I'd like to welcome you to my talk today entitled The Extraction of Long-Chain Per- and Polyfluorinated Alkyl Substances, also known as PFAS, from soil. In this talk, we're going to explore some experiments that we ran that demonstrate some interesting points about the extraction of long-chain PFAS from soil. So here's a quick rundown of what I'll be covering during this presentation. I'll begin by giving a brief overview of what PFAS are. I have a definition of long-chain PFAS, which is relevant to this study. We'll talk a little bit about long-chain PFAS in the environment and how this relates to soil spiking studies in the laboratory. We devised an experiment of sequential extractions on soil that we've used to demonstrate that pressurized liquid extraction, or ACE, is beneficial for the extraction of long-chain PFAS. We'll talk about some of our results using different extraction methods. And finally, we'll have a little discussion as to what we have been able to achieve extracting PFAS from soil. So let's begin with what are PFAS. So PFAS, or PFAS, stands for per- and polyfluorinated alkyl substances. Now, if you look to the left of this slide, I have two pictures of PFAS molecules. These are different PFAS molecules. Now, generally speaking, PFAS is perfluorinated alkyl substances, or it's polyfluorinated alkyl substances. And for each of these, you can break up the molecule into its per- or polyfluorinated alkyl chain, which, as you can see, is the long chain with the F's on it, right here. Now this chain is a perfluorinated alkyl chain because every carbon on here has a fluorine, whereas the chain over to the right is polyfluorinated because the last two carbons right here do not have fluorines on them, but they have hydrogens. And the other part of PFAS molecules are the head group. And the head group can either be ionic or it can be neutral. And it's usually polar, but not always. And so this gives rise to quite a number of possible PFAS compounds. And currently there are well over 5,000 substances that are listed on the US EPA's PFAS master list. Now, generally speaking, short chain PFAS are 2 to 6 carbons, 2 to 7 carbons. I've even heard 2 to 8. And long chain PFAS are generally 8 carbons and longer. PFAS are highly persistent organic pollutants, and they tend to bioaccumulate in not in fat, but in blood and other tissue. So for the purposes of this presentation, short chain PFAS will be C2 to C7, and we have an example down here of a C4 sulfonate. And for long chain PFAS, we're going to be considering 8 carbons to 14 carbons. And so the 8 carbon PFAS includes PFOS and PFOA, which are essentially globally regulated. Now, it turns out that around 99% of Americans have some level of PFAS in their blood. And this was tested because the manufacture of these PFAS compounds began shortly after the Korean War. And so the blood of soldiers that was taken before the global manufacture of these compounds did not contain levels of PFAS in their blood. but blood tested after did contain PFAS. And how did it get there is the big question. Well, since PFAS are man-made, then and they're highly persistent, any occurrence of PFAS in the environment is also from a man-made source. And they perfluorinated and polyfluorinated substances impart very useful properties. So they have water repellency, grease repellency, which makes them useful in carpets, outdoor adventure wear. You have waterproof tent here in the top picture. A few of PFAS are used in chrome plating in vehicles, but I would say the most popular usage would be in non-stick cookware and also grease proofing of fast food wrappings and things like that. So those are ways that Teflon and other perfluorinated products have made their way into society. Now they're extremely useful, as we all know, because of these grease-proof and waterproof properties. They're also very chemically resistant, so they've found their way into many niche applications in society. And it turns out that PFAS can be released into the environment. Now, the short-chain PFAS that we talked about are generally very water-soluble, and they are easily carried by water through soil systems. Now, I want to talk about soil systems and water because it's estimated that about 90% of the human intake of PFAS comes from food consumption. So for short-chain PFAS, they can be carried through a soil system into the groundwater, which presents its own difficulties. By contrast, long-chain PFAS are not very water-soluble, and so they don't travel through the ecosystem with the water, and they would rather stay adsorbed onto solids like soil. And when we go to measure the levels of long-chain PFAS in soil, we usually get very low yields. So what happens to the long-chain PFAS? Well, I've heard it said that long-chain PFAS are incorporated into the soil matter. In other words, they become part of the soil. I've also heard it said that they're stuck in the pores, or simply that the long-chain PFAS are gone, and these would explain the low yields that we see. But this is an interesting situation as an analytical chemist, because there are ways of testing how well we can extract long-chain PFAS from soil. And typical way to test for that is by running a spiking study. Now to do that, you would take a soil sample and you would spike it with a known amount of PFAS. Now this could be isotopically labeled standards, it could be surrogate compounds, or it could be native PFAS. The important thing is that you know how much you put in so that you know how much you should be recovering using your extraction method. So you take the spiked soil and you would sonicate it in methanol. And with optimized experimental conditions, you could expect 100% recovery. However, there's a difference between PFAS that has been spiked into a sample and PFAS that has been weathered into the soil. And so one way to look at it is that the PFAS you spike into a sample are more like they're on the soil particles. And I like to use the term lightly bound. In contrast, PFAS in the environment are more in the soil particles. And you could use the term they're tightly bound. So we have this contrast between PFAS that are lightly bound and PFAS that are tightly bound. And so just to illustrate this further, I have these brown soil particles that I created masterfully. And I'd like you to imagine that we have, in the yellow circles, we have PFAS that we have spiked in. So we've spiked it into the soil, and these PFAS are kind of on the surface of a soil particle, and they're lightly bound. Whereas in the green circles, we have PFAS, which are endogenous to the sample and have been weathered into the soil particle. So they're in there very strongly. And if you were to choose an extraction method, it's very possible that you can extract close to 100% of the PFAS that you spiked in. But that same extraction method could not be aggressive enough to extract the tightly bound PFAS. And so in this case, in this scenario, you can get about 100% recovery of your surrogates or your internal standards or whatever you spiked in to the soil sample. And simultaneously, you could get very low recovery of PFAS analytes that are endogenous to the soil sample because those PFAS are more tightly bound, whereas what you spiked in is lightly bound. And this could give rise to false negatives. So let's talk about some experiments we devised to explore these possibilities and to try and extract more consistently at high yields long-chain PFAS from soils. So the first thing would be to sort of reimagine the spiking study. So you're talking about a spike and sit study rather than simply just spike and go. So you spike the PFAS onto the soil. They're lightly bound. You let the soil sit to dry over the weekend or a few days, and presumably now the PFAS are more tightly bound to the soil particles. They're in there. Okay? And once the PFAS are more tightly bound to the soil particles, now we can explore different extraction methods. So first of all, we would use sonication or vortex, where we'd sonicate the soil sample in 100% methanol, filter out particulates, and SPE, the methanol extract if needed, but essentially just analyze it from there. The other extraction method that we would use, which is a more aggressive method to compare to sonication, would be accelerated solvent extraction, better known as ACE. And our instrument was the ACE 350. We'll use methanol as an extraction solvent at a temperature of 100 degrees. And we use 3 cycles, so 3 shots per sample, 25 minutes per sample. Okay. And our analysis was done using a Thermo Vanquish LC coupled to a TSQ Qantas triple quad mass spectrometer. And now the experiments that we ran went like this. So we set up 3 soil columns, and we spiked each column with 10 nanograms of a variety of PFAS, so acids and sulfonates and you name it. And the idea being, so we let it sit and dry, and then we rinse it through with 60 milliliters of water. And by the way, there are 3 columns. We had different pHs, pH 3, 5.3, and 10, but it turned out that pH didn't really have any effect globally on these results. So anyway, we rinsed through with 60 milliliters of water, and the idea would be to collect the aqueous eluate and analyze it on LCMS. Any PFAS that are not in the aqueous eluate are presumably still in the soil. So the idea was we would then take the soil that had been rinsed through with water and subject it to sonication, and then analyze the extract from that sonication with LCMS. Finally, we would take the same soil that we just previously sonicated and extracted, And we would subject that same soil to ACE, so a high pressure, high temperature extraction, and then analyze the extract from ACE using LCMS. And trying to compare these sort of 3 levels of aggressiveness in your extraction to see which PFAS would come out. So let's look at the results of that. Now, I only want to show you the acids right now because the acids illustrate the trend that I want to show you most clearly. So here we have 6 carbons to 14 carbon perfluorinated alkyl acids spiked in at 10 nanograms. And in the first column under percent recovery, we look at the aqueous eluate. Now in the red box, you see high yields of C6 to C9 acids. Now, pardon the 200% here. There are a variety of explanations as to why we could have 200% yield of certain PFAS in here. So I just want you to draw your attention to the trend. If you notice in the aqueous eluate column, there's very low yields of C10 to C14 acids. Now, if those acids are not in the aqueous eluate, presumably they're still in the soil. And so let's look at the result after sonication of the soil in methanol. We see we have low yields of C6 to C8 acids because almost all of those eluted with the aqueous eluate. And we see in the red box in the middle column, we have very high yields of C9 to C11 PFAS acids. So we're extracting some longer chain acids using sonication that did not elute with the initial water elution. But as you can notice, C12 to C14 have unsatisfactory recoveries. So after taking this sonicated soil, we put it in the ACE cell and we apply pressurized liquid extraction to it, and we see that we have the missing C12 to C14 carboxylic acids coming out, and even little bits of other stuff that hadn't completely eluded the column. And so the trend for us was clear, seeing this, that ACE, being the most aggressive extraction method of these 3, would be able to extract with high efficiency long chain perfluorinated acids from soil. So it's very encouraging for us to see this. And so now, today, we routinely use ACE to analyze our soil samples. And here's an example of an extracted chromatograms of a real soil sample that we analyzed. Kind of low-level sample, 10 nanograms per gram, with the exception of PFAS. So it's very, it's been very effective for us to use the ACE. Again, across the board, we routinely get 100% recovery of short to long chain. So let's do a little bit of discussion as to some places that we've gone since then, and some things that we've managed to do with the ACE. So first of all, we've run some method detection limit studies using isotope dilution quantification and the ACE. And here are just to show you some numbers for us, where we're at for method detection limits. And now method detection limit here is defined as students T for 10 samples multiplied by the standard deviation of those 10 samples at the spike level. So these are the numbers you see. Some of the numbers in red are just for PFAS that do not have an exact isotopically labeled internal standard. Okay. We can detect about 1/5 of these levels comfortably as well. And so you see we've expanded our list of analytes to 28. Linearity is excellent for all compounds except for C13 acid, and that's largely, and it's biased low, and that's largely because it's still linear, but it's biased low. That's because it doesn't have an exact isotopically labeled standard as well. Slope in R squared is great, and so this is linear between 1 nanogram per gram and 400 nanograms per gram. So quite a nice range there. And this is all obtained using accelerated solvent extraction in our process. Our blanks. I really want to show you this slide because our blanks show that there is a low level of carryover between samples. Now, to help you interpret this, we've got 3 top columns. We have 3 spike levels: 1 nanogram per gram spike, 20 nanogram per gram spike, and a 400 nanogram per gram spike. Now, the idea is here, the ACE has a shared line for all samples that you put on. And so you do have the potential for carryover between samples. However, from 1 nanogram per gram to 400 nanograms per gram, the carryover is very minimal. It's 1% of the spike level or less, and much less in the case of 400 nanograms per gram. And it's always the usual suspects for us, as you can see in red. So I just mentioned that the ACE 350 uses a shared solvent and sample line, and that has the potential for sample carryover, specifically with high-level samples. Okay, and another point, which is very relevant for the analysis of PFAS using the ACE, is that the solvent lines are Teflon. Now, Teflon, as you may know, is a fluorinated polymer, and some PFAS are common byproducts of solvent rinses in those lines. And so you risk having a background level of PFAS that might be too high for your particular application. However, as you saw on the previous slide, our background levels of PFAS are very low and are only a fraction of the spiked level that we put in the sample. And we think that's mostly due to the fact that these Teflon lines have not been replaced in 4 years and have seen many different solvents flow through them. So the background levels of PFAS are extremely low at this point. And finally, using the ACE, you're not only going to extract PFAS from your soil, but you're going to extract other substances that will form the matrix of your sample. And so quite often, whether it's soil or tissue, you need to employ solid phase extraction or some other extraction technique to clean up your sample, especially when you're analyzing it at trace levels, such as what we do at Pacific Rim Labs. So to conclude, we found that sonication was an inadequate extraction method for long-chain PFAS from soil. And conversely, ACE was an adequate extraction method for PFAS from soil for short and long chain alike. So that's from 4 carbons all the way up to 14 carbons long. And we demonstrated this using a spike and sit approach with sequential extraction experiments. Now, today, our analyte list had been expanded from that experiment to 28 analytes, and we use isotope dilution method with ACE for the extraction of PFAS in soil. And of course, analysis by LC-MS-MS. We have demonstrated a wide linear range for our analytes, low carryover, very low carryover, 1% or less of the spike level, and a low method detection limit. And so I would like to say thank you to all of you for joining me today for this presentation, and I welcome all of your questions at the end of the presentation. Thank you.